Okay, you guys. Homework. There's a box floating around the classroom for you to drop the 4-star problems into. Essentially everything that these the 11 and 13 from the 29th and 11 and 16 from the 31st will be in the box. None of the non-star problems should be in there. Those are problems that are just to guide you in your studying and absorbing this material. The WebWorks should be completed now. I think the second WebWork problem will close at 4 o'clock today. Let me just describe to you how I'll score this homework. So you'll have a couple of WebWork problems. A couple of WebWork homework sets, and I'm just going to sort of lump them all together and give it a check mark or something like that. You know, and then that'll be essentially out of 5 points. So let me put that in there. Then you've got your 4 star problems, and that's going to be out of 5, out of 5. Out of 5, and out of 5. So you've got a total of 25 points possible. For this WebWork stuff, you know, again, the WebWork exercises are more just for you to develop the skills and to give you feedback for how you're doing, you know, instantaneous feedback for how you're understanding the material. If I see a good effort on those things, you know, lots of attempts and some right answers and things like that, then you're going to get a full 5 out of 5 for that. So I don't really care if you missed a couple of them. If you missed a couple of them, you should certainly understand why you missed those. But in terms of the score on the homework, it's just going to be a 5 out of 5. It's almost like a check mark. Okay, the other 4 guys I will grade more carefully. Well, as carefully as I can for 60 students. And in the end, you'll get a score out of 25, which then I will convert to a percentage, and that's what will appear in the online gradebook once I get that set up. Okay? Okay. If you're turning in your work, you don't need to staple it together. If your name's on each sheet, or frankly, even if your name's not on each sheet, as long as they're consecutively in the pile, I'll figure out what belongs to what. You don't need to staple it. You don't need to fold the ears over. You don't need to do anything. I'll figure it out. Any questions about homework? All right. Let me go on then. A lot of you sent emails over the weekend asking me questions. Let me just clarify my email policy. If I have time and if it's fairly easy to answer in an email, I'll do it. Otherwise, you're just going to have to find me. Okay? So if you sent me an email over the weekend and I didn't answer, that's why. I just didn't feel like it. You'll notice that there were quite a number of emails over the weekend, and please do read those. I put hints, etc. in there. Make sure you read those before you send me your own email if you have a question. And yeah. I've got office hours, I've got email, and heck, you could call me if I might even pick up the phone. Okay, any questions about that? Good. So we are now into the second week. Let's talk a little bit about what's coming. I'd like to finish chapter 12 on Wednesday, and just to kind of wrap it all up into a package, we'll just do some review work on Friday. So we'll talk about chapter 12 in broad strokes, and then probably do some group work in class, just on some perhaps slightly more involved problems that synthesize lots of the ideas from chapter 12. And then we will move on to chapter 13 in here, and I will try to put an exam date on here for the chapter 12-13 exam. I'm going to just test both of those together. After that, we'll probably get an exam after every chapter, but the first 2 chapters are going to be combined. That exam will be in class, It will very, very strongly resemble homework problems that you've seen. And it'll be, I'll give you some paper and some questions, and you'll write your answers on a piece of paper, and you'll give them to me, and I'll grade them on 5-point scales or 4-point scales, I don't know. Anyway, you get the idea. So I'll try to get that date to you for the first exam by the end of the week, as I sort of clarify how I'm going to approach Chapter 13. Okay. Tabo, what was the question that you were asking me?
It's on the webway.
Uh-huh. Was it the force one?
Yeah.
Okay. So a lot of people had questions about the force one, and let me just briefly talk about the force one in general terms. So you were given a force and you were given a direction V, and the question was, gosh, was it find the component of F in the V direction? Is that how it was phrased?
It was find the work done by the vector F in the direction of V.
That was the third part, right?
Oh.
But the first two parts were find the component.
And the parallel components.
Right, okay. So we find the component of F in the V direction. That's simply the projection of F onto V. And you have that formula, F dot V over the length of V squared times V. Right, so the answer to the first one would just be to calculate that. And that's going to be a vector, right? Okay, the second one, what you have to do first, before you can do the second one, is to find what I will denote as V perp. So a vector that's perpendicular to V. And I tried to explain in an email how you would find this vector. But in general, if you have a vector V, let's say 1, 2, then you can very quickly find a perpendicular vector by reversing the coordinates and then changing the sign on one of them. It only works in 2 dimensions, but that's what we're working in, so that's okay. Yeah?
The only question was if there are 3 dimensions, wasn't it?
But one was zero.
Okay, so is it clear that this is perpendicular to this? How do you know? If you take the dot product, you get 0, and in fact, it's by design, right? Flip these guys, change the sign on one of them, and what you've done is exactly what it takes to make the dot product 0. And so this guy's perpendicular. To answer B, what do? Project F onto V perp. So you would have F dotted with V perp over the length of V perp squared times V perp. And then the last one, which I didn't talk about very much, and I told you could just forget about it, was the work problem. Work is force times distance. In this case, we treat V as a displacement vector, and you do F dot V, and that's the answer. Okay? We'll talk much more about work, actually probably in chapter 14, I think it is. No, 15. Chapter 15, I think. Okay, let's go on to today's topic, and that is lines and planes. Okay, lines and planes are geometric objects. Did you have a question, Tabo?
Yeah, about the angles and gradients, how will we know how many decimals to do?
Yeah, I know. That's to be honest, I don't know the answer to that. It seems like you're probably safe with maybe 3 places to the right of the decimal point, but it's certainly WebWork isn't telling us how many decimal places we need.
What I found that works is you don't even have to calculate all the way out. I did like cosine or cosine of like 1 over root 3 or whatever, and it did the answer in WebWork for me.
Okay.
So
you didn't use but he was asking about arc cosine.
Yeah, I mean.
So does that work also?
Yeah.
Arc cosine. So use that instead of using the calculator. Just do arc cosine of whatever the number is and input that, and I guess that works. Okay, thank you. There was another comment over here, or was that the same comment? Okay, good. Yeah, we're all learning about web work. So what I want to talk about today are lines and planes. This is section 12.5. And both of these are very useful examples to have kicking around during Calc 3. And so that's why we're going to start talking about them now. And they're intimately related to vectors, displacement vectors, dot product, cross product. So we get to play around with some of these new concepts as we play around with these new geometric figures. You're all probably familiar with lines in 2 dimensions. The equation y equals mx plus b, right? The m is the slope and b is the y-intercept. We now want to talk about lines in 3 dimensions. So I'm going to use this pen a lot today to indicate direction. And what I'd like to do is start talking about, for example, the line through this point in this direction. And when I put this up here like this, I'm talking about a line that extends infinitely in both directions. But it goes through this point, and it has this direction. Okay, similarly, I'm going to talk about planes. And we're going to try to get a geometric notion of what a plane is, what a line is, and then I want to go into an algebraic description of a line and a plane. And an algebraic description is one that involves symbols, like y equals mx plus b, which would be an algebraic description of a line in 2 dimensions. I want to get you an algebraic description of a line in 3 dimensions, an algebraic description of a plane. Okay, so without further ado, let's talk about planes first, and then we'll talk about lines. It's interesting, planes and lines, very different from each other, and yet for a plane, you need a direction and a point on the plane to define it. And it's actually true of a line as well. For a line, you need a point on the line and a direction. For a plane, get myself a plane here. Okay, for a plane, it's the same thing. I need a point on the plane and a direction of the plane. Now, the direction of the plane is not quite as obvious as the direction of a line, because you can sort of tilt the plane in any way like this, and it's not clear to me what the direction of a plane should be. It is pretty clear, if I have a point in space, here's a plane that goes through that point, and here's another one, and here's another one. There are lots of them, right, that go through that point. But it's not really clear what the right direction is. What we're going to use to describe the direction of the plane, ideas?
Straight up the y.
Not quite, because we don't really know where the y-axis is in relation to this plane. But I think you're on the right track. A vector that's perpendicular, exactly. So if I take this guy, this direction, and I take this point, okay, there's only one plane that does that, right? It's not this one, it's not this one, it's just this one. Okay, so that's what we're going to use. So planes are defined by a point P on the plane and a direction perpendicular, direction N, perpendicular. Okay. Let me draw you a picture. And let me make it a slightly tilted picture. Okay, so we've got this plane. Here's the point on the plane, P. Here's the direction, the normal direction, N. And often you'll actually see that the vector, the normal vector, is actually on. They'll put the tail of the vector on the plane like that. what does it mean for some other point Q? What does it mean? How do we know if Q is on the plane? Ideas?
You could construct another vector and see if the dot product is
Any other vector, or do you have a particular
or a
vector in mind?
From the point that the perpendicular vector is going throughout to Q.
So what's that vector called? We actually have a notation for this. QP with an arrow, yep. Like that. And how do you calculate QP with an arrow? Not the distance formula.
P minus Q.
Just take the coordinates, right, and subtract coordinate-wise. Does that ring a bell? Okay. So, yeah, okay, so we build QP. Is QP on the plane? And then somebody was saying it. Now what?
See if the dot product between the perpendicular vector coming out of the plane and the vector that we just constructed inside the plane is equal to 0.
Yes, if QP dotted with n is 0. Make sense? So we now have a foolproof method. We can pick any point in all of space, and we can test whether that point is on the plane using this algebraic description. Yeah? Okay. Let's give some coordinates here and maybe boil this down into something a little bit more familiar. Let's let Q be x, y, z, and I have to be more careful. Q is a point. So it has rounded brackets. And P is the point on the plane, which I'm going to call V1, V2, V3. And then there's N. What kind of brackets for N? Pointy ones, right? Angle brackets. So now I've given all of my quantities explicit coordinates. And what I'd like to do is explore this dot product relation using these explicit coordinates. So let's do that. The vector QP can be written as V1 minus X, V2 minus Y, V3 minus Z. And the vector N is simply A, B, C. And of course it's all still equal to 0. And we can play around with this even a little bit more. Let's see, we could write this as, we could move all of the x's, move the x and the y and the z's over to the right and keep the V1, V2, V3 on the left. I suppose we could do that. Let me blow this up a little bit more before I do that. V1 minus x plus b V2 minus x plus c V3 minus, sorry, not x, y. Like that. Yeah? What did I do there? I actually just did the dot product. Now I'm going to move the x, y, and the z terms over to the right-hand side, and what's left is a v1 plus b v2 plus c v3. On the right-hand side is ax plus by plus cz. And on the left-hand side, I'm going to call this just some number d. And on the right-hand side, I'll stick with ax plus by plus cz. Just in case I was interested in it, I could write d as a dot product, couldn't I? What dot product would it be? Kind of p dot n, there's a slight faux pas in here. P is a point. We don't like to dot points. We only like to dot vectors. A really quick notational way to convert P to a vector is just put a little arrow above it. And that means it's the point it's the vector whose tail is at the origin and whose head is at the point. Okay? Okay. And probably to be technically correct, I would have a little arrow above my n too, but I'm just not going to do it. Okay. So yeah, that D is actually secretly the vector P dotted with n. And the right-hand side you could actually interpret similarly. How would you write the right-hand side as a vector, as a dot product? Yeah. So this is just one more way of looking at a plane algebraically. Okay, let's talk about the goal here. Or what am I trying to get at here? What skill do I want you to take home today? I'll answer that question with an aside. Okay, if I say describe x squared plus y squared plus z squared equals 4, what's your answer? What do you tell me?
It's a sphere around the origin of radius 2.
Sphere around the origin of radius 2. That completely describes this equation, right? Geometrically. So the answer is it's a sphere of radius 2 about 0, 0, 0. That's the answer. Okay, let's switch back to the question at hand. Let's say instead of x squared plus y squared plus z squared equals 4, I say describe ax plus by plus cz equals d. This is really just another equation, another common equation that you need to become familiar with in this class. Just like you already know how a sphere, the form of a sphere equation, now you need to know the form of a plane equation. Okay, this is the equation of a plane. What information can you tell me about the plane just by looking at this equation? You can tell me the direction of the plane, the normal vector, right? Does everybody see that? So in the same way, how did I figure out that the radius was 2 in the sphere? I happen to know that that's r squared on the right-hand side, right? How did I know it was a sphere? Back up a little bit more than that. How do I know it's a sphere and not a plane?
Just because that's what the equation for a sphere looks like.
Exactly, because that's what the equation for a sphere looks like, and you've all memorized that, right? Or maybe you have some deeper understanding about the distance formula and yada, 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 right? But I have to say, even when I look at that, I don't really think distance formula. I just say, oh, that's the equation of a sphere. Okay? So I want you to look at this and say, oh, that's the equation of a plane. With n equal to a, b, c. That's what I want you to do. Slightly trickier question, can you get me a point on the plane? Well, if I am a point, I've got my 3 numbers, x, y, and z. How do I test myself to see if I'm on this plane? Sorry?
If D equals 0.
Actually not. D is given, right? We're given the equation of a plane. We're given A, B, C, and D. So D might not be 0. D might be 10. So I've got my x, y, and z. I'm looking at myself, and I'm like, am I part of this plane or not? How do I figure that out if I'm given the equation?
If you dot it with A, B, C, it should be D.
Yes. If I take my numbers, x, y, and z, and I plug them into that equation, and it's true, then I'm part of the plane, right? That's how all of these equations work. How do I know if I'm on the sphere? I take my numbers, I square them, I add them up. If I get 4, hey, I'm on the sphere. This thing here, I take my numbers, I do ax plus by plus cz. If I get d, I'm on the plane. That's how all equations work. I know a point is on a surface described by an equation if it satisfies the equation. Okay. Given that information, can you give me one point? There are many. Can you give me one point that's on this plane? Just stare at it and see if you can come up with one that's on the plane. Three numbers, x, y, and z, that satisfy this equation.
0, 0, d over c.
0, 0. Oops, not a vector. 0, 0, d over c. That's the candidate. Is it on the plane? Sure, because if I take x equals 0, that's gone. I take y equals 0, that's gone. I take z equal to d over c, what do I get? D, and that's what I'm supposed to get. Good. Give me another one. D over a, 0, 0. And there's one more that is easy. B. Got it? Now, when might this approach fail to produce a point? For example, let's stare at this one.
If it's 0, then you have something over 0.
If C is 0, is it possible for C to be 0? Yeah, sure. Okay. So we do have to be careful about that. Is it possible for all three of them to be 0 at the same time?
No. 'Cause
Then D would be 0. You'd have the equation 0 equals 0, and that wouldn't be a plane.
the normal vector would be 0, 0, 0.
Yeah. So that all breaks down. So at least one of these guys is going to work for you. Let's talk a little bit about let's talk about this one. Where is that point? Assuming A is not equal to 0.
Touches the plane.
It's on the x-axis, right? This is the x-intercept. This is the y-intercept. And this is the z-intercept. Assuming that it has them. Okay. What do I mean by that? Well, let's pretend here's the x-axis, the edge, the inner edge here. Here's the y-axis. Here's the plane. Is it possible for there to be a plane that does not have an x-intercept? Sure. How about like this one, right? Here's the x-axis. Here's the plane. It goes infinitely in all directions, but it never hits this axis. Okay. In fact, there's a lot of them, right? There's really only one that I have to worry about. It would be this one. That one would have lots of x-intercepts, right? Okay. And so there's a whole lot of planes here that don't have x-intercepts. And in fact, there's even more because I can do them up here, and I can do them down here, right? So lots of planes that don't have x-intercepts, tons of them. How about planes that don't have x or y-intercepts? Any of them?
Parallel to XY plane.
This one. And this one. This one. But not this or this. Or you can't have any kind of inclination towards the plane, towards the xy plane. But there's still a lot of them. But if you were counting these things, somehow there are fewer of these than there are of so you're sort of constraining them in a sense. I know, yeah. Okay, are there any planes that have no coordinate axis intercepts? No, you kind of have to hit one of them. Okay, but one is all you have to hit. Are there any that hit all three? Yeah, in fact, you can actually give me a condition. What condition will guarantee that I hit all three? Yeah, they don't have to be at the same point. What's a condition on this equation that will guarantee that I have intercepts on all three axes?
A, B, and C are 0.
None of, they're not zero. They're all non-zero. If they're all non-zero, then this thing is going to hit the plane. It's going to hit each axis somewhere. Okay, it's a little bit of geometry. Let's talk about. Well, let's do an example here. We'll do. Let's do number 3 here. I was going to do number 1, but let's talk about number 1 really briefly. Find an equation of a plane containing the point 6, 2, 1 and perpendicular to 1, 1, 1. That has precisely the information you need. It has a point on the plane, and it has a direction. It's a little bit too easy. So let's talk about 3. Find an equation of the plane containing these 3 points. This has lots of one piece of information, points on the plane, and none of the other piece of information, which is the direction that the plane is inclined or tilted. And yet there's enough information here for us to get at the direction of the plane.
Can't you make a vector like 2 different ones and then make one that's perpendicular?
So let me sort of switch back and forth here. So 1, 2, negative 3. And 0, 1, negative 2. And 1, 2, negative 2. Okay. Now, I don't know precisely what this thing looks like, so what I'm going to do is draw a generic picture to help me organize my thoughts. 3 points on the plane. Plenty of points on the plane to choose from. Continue with your discussion now.
Okay, so you could pick perhaps the first point and the second point and make that into a vector, and pick perhaps the second and the third point and make that another vector. And then we have an equation to find a vector that's perpendicular to both of those, and that'll be and you can compare it to any one of those different directions.
So is that your idea, cross product? Okay, so what we're looking for is some vector that is perpendicular to the plane. What do we know about a displacement vector between 2 points in the plane? That displacement vector is parallel to the plane. And we've got 2 of these guys. Right? We've got 2 vectors that are parallel to the plane. Okay. So now it's really just a matter of kind of getting organized a little bit. So maybe we'll take this guy. I'm going to redraw this picture a little bit just because I know what the answer in the back of the book is, and I'm going to try to shoot for that and then talk about variations on that. So you'd be happy with that method too, right? Okay. And then the vector that we seek would be this guy. Right? Okay. I have no idea where these points are on the plane and how they're related to each other. So what I'm going to do is just pretend that the tails are here and the heads are here. Okay? So I'll form these two displacement vectors. In fact, let me call this P, Q, and R. And we'll put Q here at the tail, and R out here, and P out here. Okay? And let's find, for example, let's find QP. Okay, so QP means take P minus Q, right? So we get 1, 1, -1. Yeah? Okay, and then let's do QR. So that's R minus Q. That's 1, 1, and 0. Okay? And to find this direction that's normal, call it N, I want to form the cross product. So I'm going to put an IJK up here and start doing the cross product. Okay, well, we can do that. Let's see. Blot out the first column. We have 0 minus -1. And then blot out the middle column, and we have 0 minus -1, which is 1, but there's a minus sign with that slot. And then the last column, 1 times 1 minus 1 times 1 is 0. So this is N. It's not the only N, but it's in the direction that's perpendicular to the plane. There are lots of possible N's. Okay. Now we have an N, we have a P. What do? Well, we go back up here and visit this guy. So we can build D by taking a point on the plane and dotting it with N. And we can build, well, we don't have to build anything. AX plus BY plus CZ, where A, B, and C are comprise N. So let's do that. What's P dotted with N?
The vector P?
Yeah, the vector P dotted with N.
Should be 0, right?
-1. Why isn't it 0?
Okay, because we're doing a plane by a plane that's graphing through a three-dimensional space and doesn't contain the origin.
Yeah, the vector P is weird. The vector P is just for convenience. Let's pretend the origin is down here somewhere. Then this is the vector P. And there's no reason that would be perpendicular to N, right? Okay, so I'm going to get rid of that. We don't need that. Okay. So we see that D is -1. And we see that A is 1, and B is -1, and C is 0. So the equation of the plane is that. Let's see if this is truly the equation of the plane that contains these 3 points. What should be true? The other points should be on the plane, right? Q and R. Is Q on the plane? X is 0, Y is 1, 0 minus 1 is -1. Is R on the plane?
Yeah. That's an equation for a line.
True, if we were working in 2 dimensions, that would be the equation for the line. But in 3 dimensions, you get what you get is the line and then all the z's that correspond to that line. So it fattens it out into a plane. Is it important that I used P here in this calculation? Remember in the definition of the plane, P is any point on the plane. I could have used Q, I could have used R, and all 3 of these points, they would give, actually I don't know if they give exactly the same value. I guess they do give exactly the same value. Yeah. So it doesn't really matter, P, Q, or R. Any point on the plane is going to work in this context. All right, so the only variability here, and you'll go into the back of the book. Let's check David's answer in the back of the book, because I'm not even sure if I did it the same way that he did. So let's go. This was problem 3, 12.5.3. So let me go there. 12.5.3. Okay, so yeah, he's got it in a very different format. Is it the same? It is. If you do a bit of rearranging, it's the same. And so you do have to be careful when you're looking at the answers in the back of the book. A lot of times, you know, the person who computed the answer used the different displacement vectors and did a cross product and got a slightly different normal vector. It's in the same direction, but maybe points the other way or something like that. So just be aware that that's a big issue in this particular area. The form of the answer may be different. That's why in web work, and you've noticed this already in some of the earlier web works. For example, web work says, let the first vector be the one with the positive x coordinate and the second vector be the one with the negative x coordinate. It's that ambiguity that they're trying to eliminate, and you're going to see more of that as you go through upcoming assignments. There'll be this sort of these weird little specifications, and what they're trying to do is eliminate the ambiguity so that you type in an answer that web work expects. It's hard to make an online homework system in math because there's so many different ways to represent the same thing. So, all right, let's go back to this guy and let's start talking about lines. Okay, so lines, and I'm going to put parenthetically here in 3D. It's very different. It's a very different situation than in 2D. Okay, in 3D, if we go back up to where we started with planes, a plane is defined by a point P on the plane and a direction N perpendicular to the plane. A line is defined by a point P on the line and a direction N parallel to the line. Okay, so we'll take a point P in space and we'll take a direction N, and the line through P is essentially all of those points along the line that are parallel to N. Okay. And again, that extends infinitely in either direction. So, all right, let's go back to the same problem. I have a point Q that's sitting in space, and I'm wondering, hey, is Q on the line? Okay, well, what can I do to try to answer this question?
PQ
That's a fact. Yes. If PQ cross N is 0, then Q is on the line. So if the displacement vector from P to Q crossed with the direction N is 0, okay, because the dot product detects perpendicularness and the cross product detects parallelness. So if you do the cross product of PQ with N, and by 0 here, I'm speaking loosely. What do I mean by 0 here? I mean the 0 vector. So I'll put that in parentheses here, 0, 0, 0. And I guess I, again, should be using vectors. Turns out that this is a little bit cumbersome to use. You can get to where I'm going using this cross product statement. I'm going to use a slightly simpler version of this, and we'll say that yes, if there is a t, and let's say a real number t or a number t, so that t times n, the scalar multiplication, is equal to QP. That's another way of saying that two things are parallel. The displacement vector from P to Q or Q to P, I guess we'll go P to Q. The displacement vector from P to Q, all I really want is that it be parallel to n. But two vectors can be parallel and still not equal, right? If what? If one's smaller than the other, right? If their magnitudes are different, right? So two vectors can be parallel, but not equal. Right. If they're parallel, however, can I always find a t that will make them equal? Just stretch it out until it's equal, or shrink it till it's equal. That's what this statement says, and this is the one that's a little bit more useful. So yes, I applaud your intuition for going with the cross product, and yes, you can get to where I'm going with the cross product. This is a little quicker. Okay, so there is some number t that stretches out n so that, or shrinks n so that it matches the displacement vector PQ. If you can find that number t, then Q is on the line. Okay, we'll play around with this a little bit. T times A, B, C equals, we'll just take P minus Q. Is that what we want? No, Q minus P. Oh boy. I'm going from P to Q. Anyway, okay, doesn't really matter. And we're going to use the same notation that we did earlier. So let's do x minus v1, y minus v2, z minus v3. And what I'm going to do is move v1, v2, v3 over to the left-hand side. And what I get is something that looks like that. It's convenient perhaps to talk about P plus Tn equals, and I'll just use script L of T to describe the line. And T is any number. So what's going on here with this equation? We have a point P. We have a direction, and we've got this vector. What happens when t is equal to 0? What's L of 0? Right, L of 0 means t is equal to 0. What happens when I plug in t equals 0 there? P. I get P. So where am I when T is equal to 0? I'm right here. Now, as I change T, what happens?
You move nothing down the line.
I start adding little pieces of N. I add a little piece of N. And how do I add vectors? What's the sum of this vector and this vector? That diagonal, right? So what's the effect of tweaking T? Of making T positive? I move down the direction of N. And what about making T negative? I move in the direction of negative N. Okay? That's all a line is in space, is it just sweeps out the direction N through the point P. So this is the characterization that I want you shooting for. A vector, a constant vector P plus a scalar times a direction N. P plus Tn. Okay, let me do a quick example there, and then we'll move on to the last topic of the day, which is how do you compute the distance from a point to a line or from a point to a plane? A point that's not on the plane. How do you find that distance? But let me do an example first. I want to do, let me see here. I want to do number 9 here. Find an equation of the line through the origin and perpendicular to that plane. So let me so the point, well, I'll let you tell me. Find an equation of the line through the origin and perpendicular to the plane blah. To define a line, we need a point on the line, which is in this case the origin, and a direction, which in this case is, well, it's not entirely obvious. It's the direction that's perpendicular to that plane. Let's fill in the first one first, and I'll let you think about the other one. So P, in this case, is 0, 0, 0. This is a point on the line. Now we need a direction. Perpendicular to the plane, whatever that is. We need a direction that's perpendicular to that plane. How do we find that direction?
Cross product of plane on plane with 2 points on the plane.
Well, if I stare at the equation of a plane, I should be able to pick that direction off right away. Shouldn't I?
Oh, yeah, it's ABC.
Yeah, ABC. So in this case, it's 1, 1, negative 1. Right? I mean, you've got this plane, and I conveniently, right? I want the line through the origin that's perpendicular to the plane. And conveniently, I can find a direction that's perpendicular to that plane just by staring at the equation of the plane, right? And picking off ABC. Oops. What was it? 1, 1, negative 1? Okay, are we ready? Yeah, we are. We've got the data that we need. We've got P, we've got N, and we simply need to fill in this box. So the line is the vector 0, 0, 0 plus T times the vector 1, 1, negative 1. And that, of course, simplifies that. Let's see if that's what Gashard has in the back of the book here. So 1259, 1259, yes. Okay. Again, you know, what's another way that we could have written this same line? What's another equation that would be the same line?
T, 2, 2, -2.
2, 2, -2, 3, 3, -3, -1, -1, 1, right? Any scalar multiple of that direction would still leave us with the same line. That's important to recognize. And so when you're working in this particular section, you may have taken slightly different steps and you might get to an equation that's different. You've got to sort of convince yourself that it's the same result. Okay. Let me finish today with the distance from a point to a plane / line. Okay, at first blush, this may seem a little ambiguous. I've got a plane here, and I got a point. What do I mean by the distance from the point to the plane? The shortest distance, exactly. And that shortest distance, what direction should I travel to go to the shortest distance? Yeah, it's perpendicular. Okay. And the same thing happens with a line. So here's a line through space and a point. Okay. When I ask the distance from the point to the line, I want the closest approach, and that's going to be along the normal vector, right? The perpendicular direction. Okay, so we're all clear on that. So once we have that geometric picture in our heads of what we mean by the distance from a point to a plane, it's actually not so bad to get your hands on that distance. And it's because we've built up so much machinery now to handle situations like this that it's just going to fall right out for us. So let's look at this. Let me sketch a plane. And let me let's introduce all of the usual important pieces of information. Say P. Actually, I think I'm going to call this Q to be consistent with the book. Q. And then let's say we've got a direction N. Like that. And then there's just this random point over here, call it, say, P. And I'd like to know how far it is from the plane. So I'd like to know, what's this distance? Ideas? The hint is the dot product.
Oh, actually, I was going to say we have an equation of a plane, and we have a normal vector and a point. So you do the point and the normal vector as the vector. So we draw a line using that, and then you set that equal to the equation of the plane.
Okay, I mean, what you're doing is kind of an algebraic derivation of where I'm headed. And what I want to try to do is avoid that, because it's going to get really messy.
Can you do a projection?
Exactly. So there's a project what to what?
QP on that.
Yeah.
You just want that vertical function.
Okay. Hopefully you can kind of visualize this. P is just sitting out there off of the plane. The displacement vector PQ, QP, I guess. I don't know, I should be careful with that notation, but it doesn't matter. QP. This distance is really the projection of this vector onto this direction, right? It's the scalar projection. So it's the scalar projection of QP onto N. Does anybody remember what that formula is?
Dot product over magnitude times vector. No, times vector. So it'd be AB over magnitude.
And that's squares. Right.
I'm trying to remember if that's squared or not. I don't think it is squared.
No, but I think you have to multiply by vector.
You have to multiply by vector too. 'cause
No, no,
that's-
scalar projection is what I want, not the vector projection. And I think in the scalar projection it's not squared.
Yeah, because the other one is.
Makes it a unit vector, exactly. Okay, so yeah, this is not so bad, right? Because I know what the plane is, so I know what Q is, I know what N is, and the point I'm interested in, I know what P is, so all I have to do is build QP, dot it with N, and divide by the length of N, and I'm done. So we have all this powerful machinery now at our disposal, and it can answer a question that if I hadn't thought about it this way and had gone that way, I'd still be doing the algebra. Okay, that's not a bad thing, okay? Because I will say that 99% of what mathematicians do is they do it the hard way in their office for weeks on end, and then they might even publish that, and then some other guy comes along and says, you know, this pages 4 through 6, you could actually condense that into this. And so a 30-page paper suddenly becomes a 28-page paper. And then 32 years later, some other guy looks at it and says, you know, pages 4 through 9 could be condensed using this, and it just gets shorter and shorter and shorter until you get the stuff that I'm presenting to you in class. Okay, so 99% of math is really doing the hard way. And then somebody else coming along and say, look, you dumb, you can do this. There's a famous quote by Pascal, Blaise Pascal. I don't remember who he was writing to, but back in the day, back in Europe, like in the 17th, 18th century, there were all these elite intellectuals, and they didn't do anything. They just sat around and thought great thoughts. And there weren't many of them, frankly. There weren't nearly as many then as there are now, people sitting around thinking great thoughts for whatever that's worth. And they would correspond with each other. They'd write each other letters all the time. You know, had this great thought the other day, yada, 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 and they would send it off to so-and-so, and so-and-so would read it and say, yes, very interesting, and here, you can do this. And, okay. There's a famous quotation at the end of one of these letters from Pascal to his buddy saying, I would have written you a shorter letter, but I didn't have time. What does that mean? So he's doing mathematics, and he says, I'd have written a shorter letter, but I didn't have time. I didn't have time to clean this up. I didn't have time to make this slick. This works. I apologize for its length. Okay, because there are sort of two prongs in research mathematics. There's actually finding new mathematics, and then there are these people like street sweepers that come along behind, and they slicken it up. They clean it up, they shorten it, they condense it, they interpret it, they contextualize it, they connect it to other things. And they're both important industries in mathematical research. Okay, so there's one. Let's talk about the distance from a point to a line. Let me sketch a picture for you. Same deal, let's put Q there. And we're going in the direction of N. Let's just leave that out for now. And here's P off of the line. And what I'd like to find is this distance right here. And probably the displacement vector is going to play a role, so I'm going to sketch it in there. And of course, this is the direction N, but the scalar projection onto N is not the right thing, right? The scalar projection onto N is going to give me this distance, which I don't care about in the least. I'm trying to find the distance from the point to the line, which is the dotted one. Ideas? You could do it the hard way. You could construct a line perpendicular to n. Yeah, you could do that. Yep. So find a vector that's perpendicular to n, but you have to make sure it's the right one, right? Because there are a whole lot of lines that are perpendicular to n. A whole lot of directions all the way around, and there's only one that's going to work. I drew the theta in there as a hint.
Is it the sine thing from cross product?
Yes. Okay, so this distance is actually the vector QP times the sine of theta. Agreed? It's the magnitude of QP times the sine of theta. That's perilously close to something that we already know. So there's the sign identity for the cross product of QP with n. Bring that n underneath. Oops. Running out of screen space here. Okay. That's not bad, right? If I know P and I know Q and I know N, I can get this distance. And again, just bringing to bear this machinery that we've already developed. This is what math is, right? You start off with these simple little atoms of ideas, and you just keep building and building and building and building. Okay? And we started out with these little atoms of ideas, points and vectors, displacement vectors. Then we start talking about geometry and the dot product and geometry and the cross product. And why waste all that effort? Use it. Go ahead.
Would you be able to do the same thing with the cosine for finding the distance to a plane?
Yes, in fact, it's basically in there. I just didn't do it. Okay, and you'll notice that the sine doesn't play a role here in computing the distance. Right? To compute the distance, I don't need to know theta, and it's the same thing here. I just kind of skipped over the cosine part of stuff here and ended up with this thing. If I re-derived the scalar projection, and probably should have done that, but I didn't. Oh well. Any other questions about this? There are a couple of examples in the homework and maybe one or two in the web work. And just keep this in mind while you're working on it. I'm not going to do any examples. Any questions? See you Wednesday.